All right, Benji,
Hey, I'm back.
talk some sweet physics to me.
Well, we've been talking some really high concepts, and I figured I would, instead of opening with something specific, let's just start with a broad question. What do you think is the role of science? We've talked about this issue a couple of times. What do you think?
Hmm. On the spot, I would say the role of science is to stratify knowledge. Basically, there's a difference between what we believe and what we can prove.
Mm-hmm.
Not they can often be the same thing, but science helps to distinguish between the two.
Yeah. That's actually pretty good. I think that lines up with how I feel about it. I think a scientist by the name of Becker, put it really well when he says that science is about more than mathematics and predictions. It's about building a picture of the way nature works. And that picture, that story of the world, informs both the day-to-day practice of science and the future developments of scientific theories, not to mention the wider world of human activity outside of science. Right? It's about, just like you said, it's about figuring out not only the things that we believe, but the things that we can show consistently are true, or at least that we can rely upon being, what we could predict about reality happening. And it's about being able to really say what is going on out there. Now, scientific theories, I think, have kind of a broad trend in the way that they develop, right? When and you can kind of see that if you look at the broad history of humanity, right? We started banging sticks until eventually we realized, hey, I can make this energy, right? I can make fire. I can make this thing happen because of, I don't know, the way that the universe works, because of the way the world is around me. And eventually we are able to harness that thing and use it for our purposes because we can understand the principle behind why that fire, right, happened. We are able to understand that, oh, okay, if I have carbon material and I produce enough heat next to it, it'll start to combust. It'll go through a reaction. We go from the scientific theories start with observing things and then creating small scale models of how those little pieces work. And then we realize that there's a unifying principle that collects these small models together under one bigger principle. And we have a better theory because it is able to more uniformly describe what happens in the universe, right? It's a shift from being descriptive or constructional about how we make our theories to a more principled approach to how we think about knowledge. And when you have one of the peak forms, I think, of theory is when you have a general principle that from which saying that, okay, this is true, then you can derive everything else that you observe. That's when you know you have a really good theory. We see this continuously with how science has developed, even when we realize that, the scientific theory should be a thing, right? The method of hypothesizing and testing that theory against the world and revising what we think our theory should be based on the results of that, right? We started off assuming that any logic we came up, like the Greeks did, that any logic that I could argue was correct had to be correct. And then we realized, no, I should trust the world to tell me. And from there, we've been able to really develop consistent predictions. We see that with, classical physics, the proverbial story of Newton having the apple falling from the tree, hitting him on the head and realizing, oh, okay, gravity is a thing that I should really think about. And that developed into this whole set of Hamiltonian dynamics that I could look at just a mathematical object that describes the energy of anything that I'm looking at. And from there, I can in a principled way, predict how that system will evolve. One of the, I think, really coolest examples is electromagnetism, right?
Mm-hmm.
When we first discovered electricity, right, we knew about magnetism for thousands of years, right? We used compasses to guide our ships. We were able to navigate the planet using that without ever realizing that there was this other thing, electricity, that also was attached to it. And then, you know, as it were, Benjamin Franklin flies his key out on a kite and gets zapped by a lightning strike and realizes, wait a minute, there's an extra force here. And when we were recognizing or trying to work with that, as people were trying to prod and poke how this new thing worked, the theories they were coming up with were detached from each other, right? Faraday and Gauss were all doing experiments and testing different pieces of the theory that were complementary to each other, right? The moving of a magnet through a coil in order to produce an electric current didn't have anything to do with knowing what the magnetic field, knowing how, a live current through a piece of wire would force and create electric flow, right? Knowing how electrons will move in that current and why they do. It was in the late 1800s that a guy came along, Maxwell, and said, I can show you that all of these disparate experiments belong under one theory. If I describe to you in the math of vectors and vector calculus, I can give you 4 laws, 4 rules that describe how electric and magnetic fields interact. And from there, I can derive every phenomenon in electromagnetism.
Now, when we talk about electromagnetism, what are we actually talking about? We know the obvious ones. So we rub a balloon and it builds up a static charge and sticks to us. But what are some other times that we observe electromagnetism?
So electromagnetism is, like I said, the theory that describes why a magnet decides to, when you float it in water, orient itself in a particular way.
Mm-hmm.
As we know, physically, the Earth has its own little magnetic field, a very useful thing for supporting life and letting us, orient ourselves. But it's also, the theory that we use in order to create all the wonderful electronics we have in the modern day life, right? Understanding how to produce, right, the light that my display is giving me is a complex set of equations and calculations so that I don't pump too much electricity into the device and burn it out. Everything is so sensitive when we're trying to, because our ability to predict what will happen lets us be careful. And from that, we're able to make these wonderfully sensitive devices. I can have pixels that are so small, my eyes can't resolve them. If we didn't have a theory that was that good, right, we would be stuck having to deal with much bigger pixels, much cruder devices, because you'd have to make sure that they didn't break if you even wanted to try and use them, right? And if you didn't have that theory behind it, we wouldn't even be able to create these things, create the things that on an everyday level, we just kind of take for granted. We don't think about how they're put together, right? Anyways, let me finish writing this up. Right, from these 4 laws that I've just written up here. Actually, I can tell you, in theory, how to build an electric circuit so that, it doesn't burn out. Or I can predict for you what it is that's coming from the stars when I look up into the sky. Because photons, light, turns out, are just oscillating electric fields and B fields linked together.
B field?
Yeah. Magnetic field.
Mm.
That when they strike our eyes, we perceive it as light, right? Maxwell has, I think, one of the coolest quotes when he finally finished his derivation. He was out on a date and pointed up to the sky and said, I'm the only person on Earth that knows what that is, pointing to the starlight. describing. Yes.
That's a bold claim.
Isn't it though?
Yeah.
Physicists are some cocky people for sure. Now, I think one of the coolest and most concise principles or rather, when you have a nice concise principle, what it lets you do is it tells you the fundamental objects that you should actually be paying attention to, right? With electromagnetism really well developed, right? We could tell you, okay, the things that I should really pay attention to are these two objects, E fields and B fields, electric fields and magnetic fields, knowing how those move throughout the world, knowing how they will, then that's what I should be looking to test. When I have a concise principle, not only do I have a better described theory, a more accurate theory, but I can also limit the things that I have to look at to understand the world, right? If I have no idea what's going on, I have to look literally everywhere. But if I have a better picture of what matters, what little things I need to measure, then I can focus my attention on that area, right? It's why
it sounds familiar.
Oh yeah, right? It sounds familiar because it's the general structure, I think, of science, of how we build our knowledge about things. The better picture I know of what's happening, the more I can focus less on stuff that is easy to predict under the theory and more on wait a minute, where is exactly where I should look? This is the principle that let us figure out that, the Higgs boson, the LHC, will be just in this energy range. And that's exactly where I want to look. And if I don't have a good theory that tells me where to look, if I don't have a good concise principle, it becomes very difficult, right? Our job of measuring the world in a way that lets us distinguish between the things that are true and just the fanciful theories that we come up with, right, becomes harder. To the extreme, if you don't look at all, well, you might think the world is just made of water or 4 elements: water, fire, earth, and what was the air? Yeah, that's the one I didn't say. Right. If I don't look, then any theory I come up with is in fact fine, because in my own brain I can describe how the world works. It's when you look that you start to be able to distinguish between what actually predicts the things that you'll see when you look, versus if I just, pretend in my head and say, hey, this is fine. I've got a good picture because, of course, I as a human being know everything.
And it's very easy because our brains tend to try and find patterns in everything.
It's true. I mean, we look at toast and see various religious figures because we're that attached to it. We go down the highway and look at cars and go, oh, no, that's a face, right? In the cars, because our brains have evolved in a way that, paying attention to those things were useful to us when we were
the movie
growing up.
Cars didn't help with that.
True. I would argue that Cars was able to be a movie because humans are so ready to just associate anthropomorphic features to just anything.
Right.
Now, there's a really big principle. In fact, it's one of the first principles that helped guide science, maybe not necessarily in a uniform way quite yet, in a theoretical way, but an idea that let us really latch on to something and understand our place in the universe better. And by principle, the thing you should read is assumption. We assume that the world works this way, which is specifically that if I'm looking at the laws of physics, that they are the same no matter where I am in the universe or how I'm oriented. Kind of a no preferred, what we'll call reference frame. Now, to be fair, it is an assumption, right? One of the most important things I think that you can realize whenever you're trying to develop knowledge is realize that no matter how good my theory is, there is some base assumption that I have to assume is how things work. Even in pure mathematics, one of the in pure mathematical logic, right? The most rigorous philosophical construct that we could possibly come up with. Just this idea leads to that idea. You have to start with some assumptions about how those relationships will work.
There is no sacred knowledge in science.
Right. Not in science, not in mathematics. The idea is you have to believe something's true. And that's, I mean, to be fair, that's something we have to do as humans every day, right? I have to trust that whatever I see and feel and touch is reality, right? That's an assumption. As, you know, classic Descartes, I could be tortured by a demon who could be simulating all this for me. We could look at our beautiful boy Elon Musk and be like, oh no, okay, everything is a simulation. It's all fake. Yeah, I know. I roll for a good reason. But to be fair, there's an annoying level of, you know, leeway you have to give that, because in fact, the distinction between whether I believe this is in fact real, as I'm touching my laptop here, or whether it's a simulation that some other entity is providing to me, that's an assumption that I have to make. In fact, there's no way that I can prove that. In fact, there's a whole beautiful theory work by a gentleman by the name of Gödel, who really tried.
If you're going to bring him up.
Oh, absolutely. It's one of my favorite examples. Who really tried to come up with some mathematical theory that could prove itself, that didn't rely on assumptions, because there is an uncomfortable, like a level of discomfort in having to say, no, I have to believe in something a priori without having absolute knowledge that it's true, right? And he did a lot of cool stuff. Maybe one of these days we'll talk specifically about that. I can and make it.
That'd be nice, especially if you could cover some of the more misunderstandings about it.
Yeah. So, you know, in the way of mathematics, it's the language is always a bit dry because it's trying to be so precise that it can be difficult to put it in terms of, you know, something that like a statement that people actually understand. But we can try.
Density of states versus partition function.
You know, that was a science talk and I was sticking to the script. What do you want from me?
Fair enough.
So, now, like I was saying, the reason that I said no preferred reference frame is such a big idea, is that it's kind of how we got started on this whole science bit. In particular, it is the idea that led to the first scientific controversy that we ever had. Specifically, Galileo, when he made his really good telescopes, was able to look up in the sky. And what he noticed is he looked over at Jupiter, and his telescope was good enough that he was able to see the moons revolving around Jupiter. And he realized, Jupiter's really big. Those moons are really small. So maybe it's more common for the small thing to revolve around the big thing. Huh. And then he thought and he realized, well, we've known that the sun is really big for a while. And we've also known, right? The Greeks were able to calculate that. The Greeks were also able to calculate within really good accuracy for what the tools that they had, the diameter of the Earth, the circumference of the Earth.
Several times they did it.
Indeed, with better and better accuracy. And it truly, the amount of information that you can gather about the universe with such basic tools is impressive. The Greeks that actually cared about measuring the world.
Didn't one of them basically use wells a certain distance apart and just computing the angle between the sunbeams?
So like you could just two sticks stuck in the ground straight out of the Earth at different latitudes. You can get so much information about our solar system from that. It's insane. And then he realized, well, you know, sun's really big. Earth's comparatively small, comparatively tiny, comparatively minuscule, and a blip. And he said, well, hey, maybe we revolve around the sun. Now, of course, at the time, the Catholic Church was in charge and had a very strong view of how the Bible described the world and said, no. Like, we clearly can see that the sun revolves around us. Just look up in the sky and you see the sun going across our sky. I was like, no, In fact, I believe the data that Kepler at the time was starting to collect is like, oh, maybe, we revolve around the sun in not these circular orbits, but these slightly elliptical orbits, right? For ages, the Greeks have been trying to figure out how to properly predict the motion of planets and the sun based on circular orbits around the Earth. And right, as I think we've mentioned before, it doesn't, when you try and predict how the Venus will move if it's a circular orbit, you get the wrong results. And so their solution,
unless you add a lot of circles.
Yeah, their solution was, just keep adding more circles. So it's a big circle, and then there's a little circle that it does on that, and a little circle on.
Right.
I don't remember what the largest number of circles that they ended up predicting was, but it ends up being dumb.
Billy says 72.
Oh, goodness. Yeah. So 72 nested circles needed in order to accurately predict.
And of course, they're all revolving around something that doesn't exist.
Yep.
Yeah.
I mean, and then, you compare that with the theory of, hey, maybe instead, just like how Jupiter's moons revolve around Jupiter, the big thing, in a semi-elliptical orbit, maybe there's one semi-elliptical orbit that all planets do. Oh, look, that gets me really good results, right? Just kind of like what you were talking about. We're able to use the stratification, like the knowledge is stratified into, this theory looks really, really more difficult and cumbersome to predict. This one is just simple and elegant. And there's been and follows this principle of, no preferred reference frame, no preferred viewing of the universe to get the information. Right? Physics is the same everywhere. And that principle has shown up several times, most strongly, right, in perhaps most glorious fashion, right, when Einstein looked at special relativity, right? Before, Galileo actually did a bunch of work on figuring out how the world should look for people who are moving. Let's say, I've got two people and they're playing catch between each other, right? There's a ball, he's throwing the ball, and there's some velocity that he's throwing it at some velocity v, right? How is that going to look to a guy on a cart that has its own velocity moving in the direction of the ball? Well, that guy would necessarily see the ball moving slower than what the people throwing the ball would see. That's what Galileo would say.
If he's just watching the ball.
If he's just watching the ball, correct. Right. Now, if that's the case, okay, I see things as I'm moving past them slower if I've got a reference frame that's moving with respect to whatever event I'm observing. And you go, okay, well, let me apply that to everything I could see. Well, I know that light, right, it takes some time to propagate. So, and I can calculate light based on its wave-like properties. I can calculate what the speed should be. So if I have a light source, if I have a light source, right, like, I don't know, the sun, what speed should the observer on the train see with the photon coming towards them? What speed of light should they see versus what should the speed of light that someone standing on the ground sees? Well, according to Galilean transforms, it should be the speed that the guy on the train sees is the speed that the standing still observer sees, but minus the moving observer's speed, right? That matches our everyday experience with watching balls being thrown back and forth. But it turns out, right, as we talked about at one point.
And indeed, we would even observe this. If we were to watch the color of the light, we would say, oh, it's getting redder or bluer, depending on whether we're moving towards it or not.
Right.
So it must be going slower or faster.
But instead, what happens is, as we talked about a little bit earlier on a couple podcasts, what Einstein realized is that what if, I trust my calculations in electromagnetism that always give you the same speed of light. right? The wave equation doesn't care about your reference frame. It ends up saying, no, you move at the speed of light that you will observe whenever I try to measure it is the same thing. It doesn't matter whether I'm standing still relative to the light source or whether I'm moving towards it or away from it. The speed of the light coming out of that source will be the same regardless. It gives you a different transform for how velocities add. And it leads to a lot of strange things, but it follows this whole idea that there is no preferred reference frame. Now here, instead of just the dynamics of physics, the no preferred reference frame seeks to explain when we try to measure something, a constant of the universe, something that one of these properties that apparently the universe says, no, this is special. This is something that looks the same to everyone. Here, the speed of light. And
Who says that?
what do you mean, who says that?
Who says that the speed of light is the same to everyone? Specifically, who is it that said, I think that it is this way versus the way people used to think?
Oh, well, Einstein is the one that really had that insight of explaining, as we talked about before, right? So for a while, what people were trying to realize is that, if light is a wave, then waves travel in mediums. And whenever I am moving through a medium relative to a wave in that medium, right, I should measure different velocities. And there were a couple of experiments trying to find this difference in the speed of light. And instead of finding, because the Earth is moving, if we accept that the Earth is moving in orbit, well, the Earth is moving and it's going to be moving at different velocities, whether we're at the top of the orbit or at the bottom of the orbit. So if there's some ether we're moving towards, and we can look at, I don't know, a distant star, whether we're going towards it or away from it, we should be able to measure the difference in the speed of light coming from that object. And what they found is, oh, no. In fact, there is no difference. And we were able to create more and more accurate experiments that should have been able to detect more and more subtle discrepancies between the difference in the speed of light. And every time they looked, they couldn't find anything. It was always the same. And so scientists at the time, at the end of the 1800s to the early 20th century, were trying to figure this out. And most of them were trying to adjust their theory about how the ether worked to account for this. And it was Einstein that came along and said, okay, you're trying to look at the results that you have and construct from that a more perfect theory. Here is instead a principle. If I say that every observer who tries to measure the speed of light measures it as the same, if I say that there is no preferred reference frame to measure the speed of light, then all of the weird things we observe, time dilating, potentially having space contract. Actually, that was one that he showed happened. But time dilation was something that the people studying this realized made things make more sense in the ether, but they couldn't explain why it did that. And from this principle of, no, speed of light is the same no matter what you do, they were able to say, Einstein was able to predict that dilation would in fact happen, and was able to predict more strange consequences of how the world worked to make sure that the speed of light was measured the same no matter how fast you were moving through the universe. And those weird consequences we could then go out and test and say, oh, well, does it happen? And in fact, it does. This principle of no preferred reference frame is a very powerful tool that lets us, well, as you would put it, stratify knowledge. It lets us cut through the crap of what we actually think, what we feel is true, and what we can actually say, no, this is what we can reliably use to predict how the world works, right? Now,
it seems like it would be the opposite without better understanding it. Like when you tell me that no one actually has the correct reference frame, it would seem intuitively, at least superficially, that makes it even harder to know what is actually true.
And so what one of the strange things, right? It does kind of lead to that, because people are going to, the relativity is simultaneity. My picture of the world, if I'm traveling in a jet plane, the events that I would say, oh, these things happened at exactly the same time, the reality that I would construct from that will be different from you sitting here at the table, right? And what Einstein effectively says is, as far as physics is concerned, those two differing pictures of reality, they're equally valid. And you have to come to a way of understanding the world that, allows for that. It's very
My facts
interesting.
are as good as your facts.
Yes, but in a less politically charged way. Fortunately, as far as even with the topics I was talking about of the lack of absoluteness of observed events being universally true, we can still come to a consensus on things, on classical ideas, because we move at low velocities and we are way above the quantum world. So no alternative facts here. But in a certain sense, yes.
Nice.
Always good stuff. So that was how we came about describing special relativity, one of the dominating theories of the last century or so, right? It's been proven again and again that it accurately describes how the world works in the realm that it claims to describe them in, right? The large scale, the gravitational waves, anything that's macroscopic and above. Special relativity and its extension, general relativity, are remarkably accurate, are remarkably capable of predicting and telling us how the world works. Now, we have another big theory that came about the same time by the little title of quantum mechanics. And the question is, well, what about quantum mechanics? How does it work? I think a gentleman by the name of Chris Fuchs puts it best when he says, compare quantum mechanics to one of our great physical theories, special relativity. One could make the statement of it in terms of some very crisp, clear physical principles. The speed of light is constant in all inertial frames, and the laws of physics are the same in all inertial frames. And it struck me that if we couldn't take the structure of quantum theory and change it from this very overt mathematical speak, something that didn't look to have much physical context at all, in a way that anyone could identify with some kind of physical principle, that we couldn't turn that into something like this, that the debate would go on forever and ever, and it seems like a worthwhile exercise to try and reduce the mathematical structure of quantum mechanics to some crisp physical statements. Because, and end quote.
Sounds like a lot of blah, 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 blah.
What he's describing here is, if anyone has ever talked to about quantum mechanics, one of the first things they will describe it as is fuzzy. Because quantum mechanics, whenever we pull out the theory to describe the atomic world and small objects, the fundamental building blocks of the universe, as far as our current standard theory goes, it doesn't allow us to make crisp, deterministic statements. So, for example, if I look at a ball on a hill, right, and I know, and I measure it, and I go, okay, I look at it, and I can see its position, and I can see how fast it's moving on that hill, and I look away, and I count the seconds in my head, right? I could, if I could do the calculations really quickly, right, write out the calculations and say, okay, when I turn around, the ball will be here, right? In fact, our brains are really good at doing this math for us, so that I can even have a good idea, like, say, a pitcher throws a ball towards me. I have a decent idea of when I should turn around, right? I can learn to...
Or you could chase a pop fly pretty well when you're a pro baseball
Exactly.
player.
I can... Your brain has a good way of understanding classical mathematics and what we call deterministic mechanics. I know from some initial point almost exactly, and if you have the math, exactly where the wall will end up later at some other arbitrary point in time. Because we have the math to describe exactly, the things that will cause it to change. I know if I know the forces, I know, here, gravity and air resistance having their effects on it. And then from there, I can figure out where the ball will be this is exactly, like you said, how pro baseball players will work. Their brains do the math for them real fast. It's not good. Human brain isn't good at doing explicit calculations necessarily, but it does do some learned calculations real well. And from there, I can know where I need to be to catch the ball. If I do that for an atom, and I have an atom-sized hill, okay, I look at it and I know exactly how it's moving. If I look away and then try and do my calculations real quick, what I'll find is, the ball could be here or here or here. And the best I can say among those three is, well, there's a 1/3 chance it'll be here and a 1/4 chance it'll be here, and whatever the leftover of, those two things minus one is here. So I should look at the center, right? But you're not guaranteed to find the ball there. You're not guaranteed the atomic ball there. Quantum mechanics, as far as we're able to understand it, gives us probabilities of where to find things, not crisp deterministic statements whenever we try to make a measurement, right? Because effectively what I'm doing when I look at it, look away, and then look again, what I'm doing is I'm making two measurements, right? I'm looking at the system and saying, oh, okay, you are here, okay, now you're at this other position. And I can have perfect information at a slice in time about where the atom is. But when I look away and try to measure it again, even if I had perfect information back at some point back in the past, I can't predict exactly where it will be. The best I can do is tell you where most likely I'll find it. Right?
You used that joke before. You can't trust atoms to make up everything.
So now, this has been a thing that has bugged scientists for forever. We talk about that, and it's just one of the most fun claims, right? Einstein hated quantum mechanics because it
even though he invented it, basically.
Well, he definitely did a lot of the work that led people to be like, hey, maybe we should pay attention to this quantum mechanics thing. Geez, his Nobel Prize is in fact in quantum mechanical work, not in relativity. Not special, not general. It's in fact, hey, photoelectric effect.
Yeah.
So this has bothered a lot of people. Like what Fuchs was saying, I should be able to bring down, right? This if you ever, like, if you've seen previous episodes, we've delved a little bit into it, or ever taken a class in quantum mechanics, right? The theory is very mathematical, and it's hard to. No one has done a lot of work on extracting physical statements from the very abstract structures that we work with in quantum mechanical theory. People have been trying to deal with that for ages. One gentleman, David Mermin, really called this out. He pointed out that everybody has learned quantum mechanics, agrees how to use it. Shut up and calculate. There's no ambiguity, no confusion, or spectacular success. What we lack is any consensus about what one is actually talking about when one uses quantum mechanics. There is an unprecedented gap between the abstract terms in which the theory is couched and the phenomena the theory enables us to so well account for. We do not understand the meaning of this strange conceptual apparatus that each of us uses so effectively to deal with our world. Effectively, when you're dealing with quantum mechanics, you have to step back and say, okay, here are these probabilities, and when I make a measurement, I only get one of the possibilities. How do I interpret what that means? And there are a lot of competing theories about how one should go about it. One of the orthodox interpretation is called Copenhagen.
So what do we mean when we say interpret the result?
Specifically, right, when I was talking about here, right? So let's say I've got a quantum mechanical wave function. Now, in quantum mechanics, that describes everything that I could know about the wave function. And let's say there's some result 1, possible result 2, and I've got a wave function that kind of looks like that. When I sit down and probe the wave function itself, I make some measurement. What's going to happen to the to the wave function is open to interpretation, because what's going to happen is I'm not going to get a mix of the two results. I will get either result 1 or possible result 2. Now, how you describe the functionality of that is not something that quantum mechanics as a theory without an extra axiom provides, right? When we went through how to describe quantum mechanics axiomatically, one of the last things was an axiom that said Copenhagen interpretation is correct. When I make a measurement, what'll happen is, let's say when I make a measurement, I measure result 1. So what happens is the wave function goes from where it was up top here and becomes a delta function on top of result 1. And there's no probability of measuring result 2. So if I look away and look back really quick, measure the same thing, I'll end up with the same result no matter how many times I do that, as long as I don't give what we'll call if I don't give the system enough time to what we'll call relax back into the original state, the original form before I took the measurement.
Or you don't cough on the instrument.
Right.
Yeah.
If I measure it exactly the same way, it'll collapse. It'll, according to the Copenhagen interpretation, the wave function describing the system collapses down to one result and stays there for a while. And as long as I'm observing it, it will be stuck at that result. As long as I'm constantly hard measuring that thing, I'll be stuck there. And what is shown here, right, is that quantum mechanics is currently in that state, right, of not describing to us the picture of what's going on. It's not based on a physical principle. It is the collection of a bunch of math that lets us accurately predict what happens, but not make a nice, a succinct, understandable statement about the physical world around us. What Mermin was kind of talking about here is that effectively we have constructed those 72 circles for the orbit of Mercury, or, we have constructed in our theory an ability to predict what happens, but not necessarily a physical, a crisp statement that says, like Kepler's law, the period of the orbit is proportional. The cube of the period is proportional to the square of the semi-major axis in the ellipse. Right. I might have gotten the powers wrong. Sorry, go back. Right. I don't have a fundamental principle a fundamental principle guiding how I construct the theory. Instead, what I have is a bunch of empirical results, and I'm trying my best to describe that phenomena, but maybe without that physical principle, we can't really do what science is trying to do, which is create a better understanding of the world around us.
So is there an analogy here to maybe epidemiology, where we can ask a bunch of people what they ate for dinner for 3 years and then look at their health outcomes after those 3 years, and then we can definitely say that the people who ate 15 pounds of bacon a week, had worse outcomes. But we have actually no causal information. There's nothing about that study that actually says, well, the reason why is because bacon might do this in your gut, or such and such. We have none of that knowledge from it.
Absolutely.
Okay.
Right. So this, and another analogy that's a hot topic, what we've effectively done is machine learning our way into this, where we've got a bunch of data and we say, okay, how do I predict what this is? Okay, here is the thing that predicts accurately, super accurately, what will happen in the next few moments, right? But what that box that I've created to make those prediction tells me about the world is super opaque, right? If I give a specific AI, feed it a bunch of images and teach it, okay, here's how you identify, cats and dogs and all these machine learning, all of these different images that they could see. When we have the technique to create an AI, a black box that says, okay, give me an image and I'll identify what's in it. But what that box does to understand the images that it's processing is entirely opaque. I have no idea what the AI is thinking in order to produce the correct result, even though it is startlingly accurate if I train it well enough.
Right. And conceptually, it might not even understand the concept that it's being asked to describe. It's just noticing a pattern.
Right. Right. And the argument is that Mermin lays out in his paper that, for example, Feynman loved and described as one of the most beautiful papers written, because he describes out a challenge for the scientific community to be able to succinctly describe what's happening in this odd quantum mechanical sense so that a general audience could understand it. Because if science can't make statements that a non-expert can understand, then really we're not disseminating and understanding the principle well enough to actually say that we know it, right? It's a common thing. My advisor likes to say, if you can't describe what you're doing to your grandmother or to your 5-year-old kid or nephew, then maybe you don't understand what you're doing well enough. Right?
If you can't explain it like I'm 5.
Exactly. To truly understand something is to be able to succinctly describe what it is that matters about that in a way that anyone can understand. Now, I brought this up because just like as has been wonderful, right? Google has given me a couple of papers that I found that are just like, hey, these are interesting topics for you. And one of these papers that I saw was in 2020, published by Stuckey, Silberstein, McDevitt, and Lee. And they propose that you can make a principled statement about quantum mechanics by using the idea of no preferred reference frames, that the measurement of Planck's constant, which is a very quantum mechanical thing, we'll get there, is in fact the way to make crisp, succinct statements about why we see this quantum fuzziness. They do this in their paper titled Answering Mermin's Challenge with Conservation per No Preferred Reference Frame. So that's a bit of a title. In particular, Mermin lays out that challenge of describe the oddity. So let's go over what that looks like. So Mermin, in a paper in, I believe, 82, lays out the oddity of quantum mechanics via one of its unusual consequences, a popular topic, entanglement. Right? Now, entanglement is kind of Bell's theorem adjacent. Bell's tells us that we have to deal with the fact that it in fact exists and it can't be explained classically. But Mermin here, in the pursuit of making a general argument that anyone can understand, right, puts together a simple device that the formalisms of quantum mechanics do not provide a clear model of what's physically happening or describing the underlying physical principles to resolve the conundrum that you see in this device. So the answer to this challenge, right, being able to succinctly describe what's happening, should give us an answer that helps us say what's really going on here. It has to do better than what's currently accepted with the Copenhagen interpretation, often called the instrumentalist approach, because that's effectively saying, when someone asks you, well, yeah, but what is physical reality? And responding, shut up and calculate it. Right? That doesn't tell you what's going on. That just tells me some math. All right. So Mermin's device works like this. Go. And is going to look like this bad boy. So what happens? There is a device at the middle that gives you a source that is a source of a pair of particles that are sent off, a pair of objects that are sent off to Alice and Bob. All right. Alice over here measures with her little machine, and Bob over here measures with his machine. And each of their machines has 3 settings. Okay. They can measure in setting 1, 2, or 3, and they are each independently capable of choosing which setting that they choose to measure. Whatever Alice chooses is completely independent and has no bearing on whatever Bob chooses. And what they'll measure with their machine is when the object that the source sends them reaches them, they'll either get a red result or a green result. And the question is,
what does that mean, though?
Well, this is just them measuring reality in some way, right? This is an abstract example here.
Okay,
we'll get there. Now, Mermin says, okay, this device gives us results that follow. I think that's the right one. That follow this grid here, right? So there are two important cases that really matter. It's when Bob and Alice decide to measure the same setting at the same time, and when they decide to measure different settings, right? So if Bob and Alice both measure 1, or if Bob and Alice both measure 2 or 3, we'll get case A. And any combination where it's differing numbers, right? Bob measures 1, Alice measures 2, or, 2 and 3, etc. The results of the experiment, the probability that Alice and Bob will get red and green results follows this chart. So let's look at what this is saying, right? Case A is saying, okay, when Alice and Bob, let's say both measure 1, 1/2 of the time, Alice will measure red and Bob will also measure red. None of the time, when Alice measures red, Bob will measure green. Bob will never measure green when Alice measures 1, when they are both on the same setting. And 1/2 of the time, if Bob measures green, well, then Alice will also measure green. And none of the time, if Bob measures red, will Alice ever measure green. So what you'll notice is in case A, Alice and Bob both measure the same thing every time, as long as they're both set to the same setting.
And where is the distinction between setting 1, 2, and 3 on this chart?
It's just this piece here, right? As far as so what we were just
piece? What piece?
The little arrow, right?
No, the chart.
So case A. So this is what is true for Mermin's device across all possible measurements, all possible settings. So case A is when they are both in 1, both in 2, both in 3.
Okay.
Right. This accounts for all 3 of those situations.
Okay.
Right. And
case B is when they're not measuring the same thing.
Right. When they're measuring different.
Okay.
Right. And case B is a little bit more complicated. And in fact, you can have results that are off. When Bob measures red, right, Alice 1/8 of the time will measure red as well. Same with green. When Bob measures green on a different setting than what Alice measured, then they'll both agree that they saw green about 1/8 of the time. 3/8 of the time, they'll disagree for each the red and green result that they could have, right? And the question is, okay, from this, I can say 2 results. When Alice and Bob's are the same in a given trial, their outcomes are always the same. 1/2 of the time it's red, 1/2 of the time it is green. And when Alice and Bob's settings are different, the outcome will be the same 1/4 of the time. 1/8 red, red, 1/8 green, green, right? Both will measure green. Okay, so here's an important question, right? The Mermin asks, right? The particles that pop out. How do I account for the fact that both, no matter what setting I choose, if Alice and Bob put their machine to the same setting, they will always agree? How do I account for the fact that the detectors always flash the same colors when the switches are set into the same position? Since the 2 detectors are unconnected, there should be no way for them to know whether Alice's is a switch is set to 1 and Bob's is also set to 1.
Now, are the particles entangled?
So we'll get to that. Yes.
Okay.
Mermin is effectively, without relying on the language of quantum mechanics, describing what happens in quantum mechanics.
Okay, so he's built a machine and he's the one that's set. these probabilities. This isn't an empirically determined probability. He's saying this is the way the machine will operate.
Effectively, what we're describing here is what we see whenever we create a quantum mechanical that relies on entanglement. But he's just trying to describe, no, there is a machine that does this, that gives you these results. How do I explain the fact that I always agree? And then how could I possibly explain both results? Right? That's the argument that Mermin is going to be walking through. Right? And like we said, there's no way for them to know for either device to know what the switch is set to on the other device, right? And yet they still agree 100% of the time, even though Alice and Bob have complete independence of how they set their switches. So the question is, how the heck do you explain that in a physical sense? Why do they know to always agree, even though they are separated and far away from each other? Well, Einstein and a couple others proposed the idea of local hidden variables, that effectively there are some instruction sets that the particles, the things at the source agree on while they're at the source. And
like, I'll spin this way, you spin that way.
Exactly. I will give red, and you also give red for setting 1 or setting 2.
I see.
Right. So, right, the idea is is that the particles would agree upon some instruction set and basically say, okay, if I see setting 1, I'll flash red. If I see setting 2, I'll flash red as well. And if I see setting 3, I'll flash green.
So you're giving the particle the power here, not the machines that were set up ahead of time.
Right. Because whenever the machine is asking the particle effectively whether it is red or green.
Okay. So the particle encodes the knowledge of red or green.
Right.
Okay.
Right. This device, right? Because that's, in science, whatever we're doing, we don't say that the apparatus measuring has the power to determine what it reads. It's okay, I'm asking where is the ball with, my ruler. The ruler doesn't have any power. The ruler just asks the ball where it is, and the ball says, I'm here. Right? Same thing with this device. The device that Alice and Bob have are asking, are you red or are you green for whatever setting that I have set up? Now, you can't prove that there's no other way to necessarily come up with a way to account for case 1, case A, where they agree as long as the switches are set to the same thing.
Because intuitively, I would think, well, the machine will just react a certain way depending on the way the particle is.
Mm-hmm. But it's not a question of whether the machine will react to a single particle a particular way, because it does. What it is why do the two machines, the two measuring apparatuses, agree when when they are separate from each other, right? Why do they agree when they happen to have the same setting, the same position for their switch, even though there's no way for the two machines to know that they are in the same setting?
So these machines are definitely not made by the same manufacturer on the same assembly line.
Right.
And put together around the same time.
Right.
These are two totally independent machines that have not collaborated ahead of time.
Because there's no reason that I can't construct that, right? I can't, there's no reason to assume physically that I can't go to one distributor and say, okay, here, make me this machine, and go to another distributor and here, make me this kind of machine, right? That would be a massive conspiracy theory.
Okay.
Right. So here, we're assuming that, the machines are created in such a way that they aren't collaborated to give you, the red, green.
Okay. So what we're saying is that the machine on the left is not set up, hey, if a blue photon comes in, light up red. If a orange photon comes in, light up green. Right. Like there are no rules established the way the machine. Basically, Alice just created a machine that does what she wants it to do, and Bob just created a machine that does what he wants it to do.
No, because it's no. I am saying that when a thing comes in, okay, when whatever particle is from the source here, right? The source here comes in to my machine, right? If it's a red particle, right, in that direction, in whatever setting they have, then flash red, or it could be a green particle.
Okay.
Right there, we're giving the particles that come out two possibilities. that they could be, and there's various ways to there's 3 different ways that each machine could choose to try and measure that particle.
I see.
Right. And so
this is, they're doing basically an indirect measurement. They're not actually saying, are you red or are you green? Because that would just be one simple thing. They're doing something else, like, do you knock electrons off my atoms when you hit me, type thing, or something else that might casually infer the color of the particle.
No, because it could still be a direct measurement.
Okay.
Mermin here is describing it in, again, abstract, non-physical terms. We'll get to a physical implementation, and it'll be able to be more direct in this. The entire point is that Mermin's trying to put together a device that can be understood without relying on physics that describes what happens when we actually do measure, for example, photons, right? If I have send out a pair of, what we'll actually find is that the way that you do this is you create entangled particles that are entangled via their spin, right? And we can say that, oh, okay, the combination of them two gives you 0 spin or gives you 1 spin or something like that. And that'll force them to, when you measure in the same alignment, right, that'll force them, if one particle is spin up, the other one has to be spin down, for example.
Okay.
That's kind of the same, what is happening here, but he's not putting it in so many words, is that, okay, how do I describe the fact that when Alice and Bob have the same setting, when they are measuring the particle in exactly the same way, that's what the switch corresponds to. The way it corresponds to the way that their machine is measuring the particle. That because of how the source is, right, the source here, we'll use the language, entangles them. Why do they agree upon, oh, okay, we both got a red photon, even though, they're 2 different photons, or we both got a green photon, right? But when I change the setting, right, when they have different settings, one's on 3 and one's on 1, the rate at which they agree drops. It's no longer 1. They don't always agree. Instead, they agree about half of the time, or excuse me, a quarter of the time.
Okay.
Right? And so what Einstein, right, and others have proposed is this idea of the particles agree on what they're going to respond when they are asked, are you red or green, for the 3 different ways that they could be measured ahead of time.
Okay. All right.
Right. It's a predetermined, there's no fuzziness. It's just like, no, here are your instruction sets. So, right, if for example, I have red, red, green, right? The instruction set that they agree on, that the 2 particles agree on, they say, okay, if it's setting 1, then we will give red. If it's setting 2, we will give red. And if it's setting 3, we will both give green. And this allows for us, if I have that particular instruction set for the particles, to exactly account for case A. If Bob and Alice happen to have the same setting, measure the same thing, they will agree 100% of the time on what they see the result being, right? Mm-hmm. They will 100% agree, oh, okay, if we were both on setting 1, we both saw red. We both saw red on setting 2, and we both saw green on setting 3.
Right.
Right. This guarantees that case A, right? The probabilities that I have for case A are guaranteed that all the time, assuming that your instruction set allows for, a 50-50 distribution between red and green, that I will have always an agreement. Alice and Bob measuring the same thing, get the same result. Okay. Now the question is, okay, what about when they don't agree? Right? So here, right, for example, it's possible that when with this instruction set, for example, that if Alice chooses to measure 1, right, she will see that the result is red. If Bob measures state 2, he will also see red. So setting, 2, 1, right? Or setting 1, 2 will give them an agreement. The same thing if they swap, right? If Alice does 2 and Bob does setting 1, they will both get red as the result. Now, that's with a the configuration like this, with that instruction set, 2 out of the 6 possible configurations that correspond to case B, 2 out of the 6 possible ways that Alice and Bob could measure different things, they will agree a third of the time, right?
Mm-hmm.
And what's interesting is if I have instruction sets where 2 letters agree and 1 is different, they should agree a third of the time at the very least. The only other possible instruction set that you could have are where all 3 instructions are the same, right? Would be instruction set red, 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 or green, green, green.
Mm-hmm.
And in that case, right, either of these cases, they will agree 100% of the time. They'll agree 9 out of the 9 possible times. So question is, so then the instruction set says, okay, at least a third of the time you have to agree, right, with each other. At least, because there's no instruction sets that I can make that create less than a third agreements. In fact, if I say, right, there are 8 possible instruction sets that I could create, right? I've got three different slots, and I can put 2 choices.
You didn't list them all out.
Oh, it's tempting, but that's just too much dry space. If I assume, right, and what we've not said is how often do any of those instruction sets show up? Maybe the universe always picks one or the other. But since I don't have any knowledge about that, the best I could do is say, okay, let's just say maybe they show up at even frequency. So all of them are equally likely. Each of the 8 possible instruction sets that I could construct are equally likely. If I allow for that, right? If I say, okay, that's the instruction sets that reality believes in, then the result for case A and B, right?
And to be clear, we're still in the local hidden variables realm. So this bottom chart is based on local hidden variables existing.
Yes. Based on there being some sort of instruction set. So instruction set. And this is what we'll call Mermin's device, the actual result of Mermin's device. The instruction set, if they are equally likely, right, if the instruction sets are equally distributed, then this is the result. That Alice and Bob will, in fact, when they measure the same setting, when they set their device to the same setting, so they measure whatever particle they get the same way, they will agree 100% of the time. Half the time they'll see red, half the time they'll see green.
So the implication here is the particles are 50% of the time they're red, 50% of the time they're green.
Right.
In either scenario.
Right. If I choose, so Mermin, when he proposes his device, says, yeah, this is what we see from the device. How do I account for the fact that I see half and half on these settings, and that I get these particular results when I have different settings? And the way that some people say, okay, maybe we can try and describe what happens here by having hidden instruction sets that we don't have access to, but the particles agree upon at the source before they get sent far away to Alice and to Bob. And if I allow for those instruction sets being evenly distributed, what I find is, okay, the instruction set allow for me to agree on case A, but case B, when they measure different settings, the amount of time that they should agree, right, is 1/2 the time as well. Is 1/2 the time, right? Because a quarter of the time, when they have different settings, Alice and Bob will both measure red, and a quarter of the time, Alice and Bob will both measure green. So half the time they will agree.
Right.
And if I had a particular instruction set showing up, the worst I could push that to would be that they would agree a third of the time, right? So if instruction sets actually dictate what's happening between these two particles, if they agree on how they are going to present their results, right, when queried with either 1, 2, or 3, if they agree at the source and then travel away and, respond, get their story straight, as it were, then the amount of time they will agree has to be at least a third of the time. But when I look at Mermin's result, Mermin says, no, my device only agrees a quarter of the time. So Mermin's device agrees too infrequently for instruction sets to properly account for both Mermin's case A and case B. Right. So when I try and construct a way of accounting for the fact that the particles agree 100% of the time in case A when they measure the same, I cannot do that in a way if I want to. I can't think of a way where the particles agree at the local level what they're going to do without throwing away the ability to reproduce case B when they don't measure the same thing. Right? It's the fact that while these two sets agree, these two sets don't agree, and that tells me the theory behind the instruction sets has to be wrong when trying to describe Mermin's device.
And again, Mermin's device is a hypothetical device that's based off empirical results.
Right. So it's
so that
abstract
3/8 is something we've already observed.
Right. It's an abstract device that Mermin is putting together in order to try and strip away the particulars of the physical theory we're describing so that a general reader can look into it without having to know what an electron is or know what a photon is. Mm-hmm. But since we're asking about that, how would one, right? It doesn't even matter if you can't construct Mermin's device in reality. Well, here we go. The way that you construct Mermin's device, as we've seen a couple of times, is something called a Stern-Gerlach machine. Right? So, that's good enough. It's something called a Stern-Gerlach machine, where Alice and Bob where I have a source of entangled particles, where these particles have quantum mechanically have a spin, right? And Mermin's challenge for his machine is, can you translate the elementary quantum mechanical reconciliation of cases A and B, where we agree upon the results all the time when we measure the same thing, and when we don't measure the same way, that we have this particular probability distribution of agreeing or disagreeing? Can I translate those into something that's meaningful to a general reader struggling with the dilemma that this device presents? Right? That is the challenge. And it shows that we are in a spot where we are able to only describe what's happening without giving a principled reason about why it happens that way. And we can see this, like I said, you can construct Mermin's device in physical reality, right? If I have a source of entangled photons that are entangled via spin, and Alice and Bob have these Stern-Gerlach machines that they can rotate, right? Then Mermin's device corresponds, the three settings that we had correspond to, right, the three possible into three orientations that I could put the Stern-Gerlach into, right? I have free rotation of this, and let's actually make it black, right? I can rotate, right? Alice or Bob freely can rotate the orientation of their magnets, right? And when the particle from this source comes out, they will either spin up or down. They'll split into two different possible orientations. And
what, based on their charge?
Not on their charge, based on a property called spin, which is a quantum mechanical property we'll get to in a sec. So basically, each atom or electron, each quantum mechanical thing, is the idea that has a thing that I can measure that spins, or excuse me, that acts like angular momentum. But we know that theory, this is how magnetism is built up, is that the spins that make up a piece of iron, right, when they are all aligned, they'll have this giant collective moment that I can feel on the microscopic level, right? But I can measure this for individual particles as well if I have a big enough magnet, right? If I have a big enough chunker, that's enough to separate spin electrons that are spin up versus spin down. In fact, we'll get to how this is done in a moment. Now, here's where we come into that the whole premise of the paper that Stuckey et al. Propose is that, hey, I can answer Mermin's challenge, this challenge of how do I reconcile case A and B with crisp physical statements that are meaningful to the reader, by saying there is no preferred reference frame. There is no preferred, and specifically, no preferred reference frame here means that everyone will measure Planck's constant in this experiment, regardless of the orientation of the Stern-Gerlach magnets that they have in their, which correspond to different reference frames. Why? Well, that's because in quantum mechanics, the possible spin outcomes are plus or minus h bar over 2. They represent
H bar?
H bar. We'll get there. The idea is that this represents a fundamental unit of information that can be, that is described, right? That can be thought of in terms of a couple of guys, Dyack and Bruckner, put out a way of reconstructing quantum theory in terms of information theory. And the very first axiom that they run into is that an elementary system has the information carrying capacity of at most 1 bit. And then different Stern-Gerlach magnet orientations relative to the source of particles constitutes different reference frames for quantum mechanics, just as different velocities relative to the source of light constitute different reference frames in special relativity. And so the idea is that when I'm measuring this quantum mechanical system, I can get at most 1 bit, which would be the distinction between up or down. That's what a bit of information is. Now, we shouldn't be surprised that the idea that no preferred reference frame leads to some counterintuitive results or mysteries, right? We've seen that before with special relativity, with time dilation and length contraction, another weird thing. So it shouldn't be any surprise that quantum mechanics has a mystery with the measurement of Planck's constant as well. So the basic principle is that whenever I measure a fundamental constant of the universe makes sure that I measure just that value. Just like in special relativity, when I measure the speed of light, I see that no matter how I try to measure it.
And what's that value?
I don't have that on hand. It's...
Oh, I don't mean the actual...
Oh, Planck's constant?
No, I don't mean what's the actual value. So we're talking about Planck's constant.
Yeah, okay. Exactly. That's, in fact, what I'm transitioning to. What is Planck's constant, and why does it even matter? Well, it was first proposed by, well, surprise, surprise, a dude by the name of Planck, right? And what was he doing? Well, back in the early 19th century, more the late 19th century, late 19th century, late 1800s. Right, we had E&M and we had classical mechanics as Newton proposed it, and it was doing a really good job of explaining the physical phenomena that we saw. But there were a few stickler points that those theories couldn't quite explain.
So we had Maxwell equations, the things you showed at the very beginning.
Right. We had Maxwell's equations. We had Hamiltonian dynamics for classical physics. So we could really describe balls rolling down hills and light coming off of stars and light sources. But one of the things that it couldn't describe really well or explain is something called black body radiation. So what does that mean in a physical sense? Well, think about if I took a pot and stuck it in the oven and made it real and turned the oven on, right? Or actually just the heating elements of the oven itself, right? As I run electricity through it to make it hot, I realize, wait a minute, of an electric oven, not a gas oven. I look at those coils and I go, as I heat them up, they start to emit light. They start to emit radiation. And what's interesting is that that's true for any object that you heat up to sufficiently large temperatures. You will see it radiating visible light. Now, physicists being physicists, the thing that we're going to work with in our theory is the most ideal form of that, right? If I want to know how a cow moves, well, first I assume it's a sphere, right? Here, the thing that the spherical cow is something we'll call a black body, right? You can kind of think of a black body. One of the best examples is to say, okay, a black body defined is something that absorbs and emits all types of radiation. It does not pick. So it will, any light I shine, any radiation I shine into it, it'll absorb, and then it'll eventually kick out. One of the easiest ways you can think about that is just think of a box with mirrors all on the inside and a tiny, tiny little hole. And if I shine any amount of light into it, it might not come, light doesn't care about the side of the hole. It'll go in the hole. So it'll be absorbed by the black body. And since it's covered with mirrors, the only time that light, right? I know mirrors will cause it to reflect and bounce around. The only time it will stop is when it bounces back out that hole, being emitted, right? So a black body can be kind of thought of this. It will absorb and emit exactly, whatever is given to it. Any radiation is given, it'll accept. Any radiation that it did get, it will kick out without, transforming too much. Now, what we noticed is that if I used my classical arguments of, how photons, how electromagnetic waves, things that are light, behave, if I tried to describe that, something called the ultraviolet catastrophe happens, which is this line here, this black line on this graph, is that if I calculate what my brightness should be based on the wavelength of the light. Actually,
Now, have we explained how the energy of the photon is correlated with its wavelength?
Nope.
Okay.
Nope. Because according to classical theory, and we'll get there, according to classical theory, the only thing that determines the energy of light is the intensity from the source. As far as E&M is concerned, the only thing that matters is the amplitude of the wave, not the frequency that the electromagnetic wave is wobbling at.
We're going way back. Okay.
We're going way back. And so they said, okay, well, if I care about the brightness, i.e. the energy, based on wavelength, right, as a function of, the temperature that I raise the black body to, then what I should find is this formula here. 2 times the speed of light, Boltzmann's constant, which is a thing dealing with statistical mechanics. Here we'll just treat it as just a number that we happen to know. Mm-hmm. The temperature that it's at, and divided by the wavelength raised to the 4th power. That's fine, but is any elementary algebra person, anyone who's taken elementary algebra will recognize, wait a minute, if I crush the wavelength down to really, really small, approaching 0, that really blows up. That gets huge. That diverges towards infinity as I crush the wavelength down. And so, what that would mean is I would get photons of small amounts of energy, of small wavelengths of infinite energy, right? That should naturally just pop out anytime I heat it up to any temperature. It's like,
So just to clarify here, what we're saying is that when I heat something up, I expect it to emit a spectrum of radiation.
Mm-hmm.
And the problem we're saying here in this equation is we would expect anything, because there's an infinite number of wavelengths
Yep.
available, that we should have an infinite amount of energy coming out of a black body.
Right. The ultraviolet catastrophe is that this black line here, that as you look at the spectrum that anything that you heat up would emit, that according to classical arguments, according to what they knew at the time, that the energy should blow up, right? That you should in fact see infinite energy from anything that has any amount of temperature on it.
Yeah, right. And the sky should be pure white, and
Right.
we should all be bathed in radiation before we're even born.
Yes.
Right.
Right. And that blows up in what's called in the UV spectrum, right? That's where you get like really shrunk down. And it was called the ultraviolet catastrophe because it was such a terrible breakdown of what the theory predicted and also what we actually experience, right? If looking at this picture, right, the blue, green, and red lines correspond to the spectrum, right? The collection of the wavelengths that I actually do observe from bodies heated up to that level, right? If I heat something up to about 5,000 Kelvin, then I expect to see mostly yellow light, a little bit of UV, and some other stuff, they're radio waves or whatever, but of decreasing intensity from them. So the reason that this was
that
fixed,
equation is probably being covered. Oh, it's not? Okay.
No, it should be fine. So obviously that was a big thing for theorists to try and figure out and go, how do we fix this? How do we get our theory to actually properly predict the data that we see in reality, right? Because that's what we've shifted towards, trusting data as the ultimate arbiter of what is true, right? So the way that this was eventually resolved was thanks to the work of a guy called Planck. Planck said, okay, well, what if instead of the assumed possibility of all these wavelengths, any indivisible amount of wavelength being emitted by this, what if the amount of energy that a black body could emit or receive was discrete and came in multiples of a particular constant? He said, okay, what if it is E H mu? So where frequency of the light, the inverse of the wavelength basically, determines the energy that a packet of light could deposit. And doing this, saying that, okay, there are discrete multiples in which one is able to add or subtract the energy from a black body, he was able to come up with this formula where this new constant h shows up. It's 2h times the speed of light squared over the wavelength of the light raised to the 5th power, but now with a new term, 1 over the exponential function raised to h over c lambda kBt minus 1. And what that reproduced is, in fact, the kind of curve that we would expect to see in real life. In fact, here's an example. One of the most useful black bodies that we ever did have is the sun. If I look at one of these days I need to come in and make sure that they get loaded in big enough right away. Anyways, so what we can see here is from the yellow data, from the yellow bars, this is what the actual solar spectra looks like. This is the frequency, the intensity of wavelengths coming from the sun, right? And the gray is this prediction of what a black body raised to the sun's temperature should be. And there's excellent agreement between the two, right?
Yeah, and interestingly, these lights are set to CCT of 5600 Kelvin.
Yeah. Gives us nice normal sunlight. So not only did Planck's law describe what we saw on a small scale and save the ultraviolet catastrophe, it matches the data that we see in real life, right? From even pretty well, even the things that are, close to being black bodies, even if they aren't perfect, right?
So he took the initial equations or the existing equations and said, look, let's stick a thing in here that is a constant, and then let's rework it a little bit.
Let's make the assumption that the amount of energy that a black body can accept or kick off is a discrete amount that is in multiples of the wavelength of light that it does kick off. Right. One of the important things, right? Because the
Do you have the old equation still up? The one that's wrong?
Right there.
There you go.
Right. So we went from thinking this is what classical theories predict to this is what Planck suggested. And it fits the data much, much better. Right. Now.
Yeah, so it's not an intuitively obvious
not
difference.
at all.
I mean, there's a significant amount of rework here.
Right. The notion of allowing energy to be accepted in discrete amounts leads to such a rework, right, of the equation that there almost certainly would be no way that you would be able to, from the principles of classical theories, be able to modify and think about, small modifications of that in order to create the one that actually predicted the data. It required a shift in the way that we thought about reality. A huge shift in that. Yeah. And without that, we basically never would have been able to get that result without something as unintuitive as saying, hey, maybe light, adds its energy in discrete packets, discrete particles. Now, the reason that this makes sense and people rallied against it for a long time is because it's very easy to show that light follows a wave equation, right? In fact, if I take my Maxwell equations, I can pretty quickly, if I have no sources of electric field, or moving current, then Maxwell's equations become a lot more simple. All right. E cross B. And they tell me that the way that E and B, electric and magnetic fields play with each other as they're changing, right? The changing of one will create the other. And in fact, if I say, okay, let's take this rule here and let me just do a little vector bit to it. Let's say, okay, I have the cross product of an E field, right? From Maxwell's equation, I can substitute this guy here, this E cross B, with the notion of B field. So I'll get, okay, X cross negative B dot dt. Now, this operator here cares about space, this del operator, or Laplacian operator, which is basically derivatives with respect to space. And here, this is derivatives with respect to time. Those things don't care about each other. So what I can do is I can swap them and say, oh, okay, here I will take the time derivative of the cross of B, right? And stick a minus sign in there to make things accurate. And again, apply Maxwell's equations and say, wait a minute, the cross of B is this E field here. So I will end up with a 1 over C squared, a second time derivative of the E field here. Now, mathematically, since I'm working in vector calculus, I have one relation that I can say, which is that if I have some vector field V, then the cross product, the space derivatives crossed with the space derivatives of a vector field can be thought of as just the gradient of the dot product minus the second space derivative on that vector field. One last time. So if I apply this to my left-hand side of this equation, right, I can say, oh, okay, this, instead of V in here, I can say should be all E's. And now what I can do is I can look at this and say, hey, according to Maxwell's equation, this is 0. Because the derivative of 0 is just going to give me 0. 0 stays a flat line.
And for those who want a little more background on this would be the first semester of undergraduate E&M.
Right. Yeah, you might get into it fast enough. Since this includes time dynamics, it sometimes is pushed to the second semester.
Right.
Yeah. The difference between statics and dynamics. While, everyone, the only thing you're really going to be interested in is dynamics in a, actual scientific sense. Getting through the theory to it can take a little time. And in fact, it's often useful to describe things in terms of the picture you'll have, right? Oh, and there should be a minus sign on this. So with with that said, I can say that, these two things equal each other. And so what that means is that I can say with crisp statement that the second derivatives of the E field with respect to space relate to and are equal to 1 over the speed of light squared of the time derivatives of that same field. And I can do this equally for B field as well, right? I can go through the same step and get this equation here for B field as well. And what's so special about this equation? Well, this is the equation that describes waves. This is what we were talking about. This is what we talked about one other time. This is the wave equation.
So basically how something is going to evolve in space is directly equal to how it evolves over time.
Right. The acceleration that something will experience, right, the second time derivative of that thing, is related to how it evolves just if I look at that thing at different points in time or in space itself. Right. So I can look at how it evolves in space to know an understanding of how it evolves in time. Right. Because usually what this is used to describe, for example, is, some sort of wave. And the way that we normally physically make sense of this is having the waves extend everywhere. So I can look at any point in space and I'll get some information about it because I'll be able to find the wave. And I can also, since it continues throughout all time, I can let it evolve, and if I take a snapshot of the wave at any point in time, I'll still see the wave. So there's no point where, I look and just see empty space with no wave. But what that means then, right? And this is why it's difficult to try and talk about how a wave, this thing that, as far as the math here says, should exist through all time and all space, right? As long as I have this light on, it's constantly sending out this electromagnetic wave to me. I should, as long as the light is on, be able to see this type of structure, right? But if it's discrete, right? If it can send in discrete elements, I should also be able to isolate it to where it shows up in space, right? And that's the fundamental juxtaposition that the idea that Planck proposed that black bodies could accept and emit energy in the form of light in discrete multiples. This is why it flew in the face of the conventional theory at the time.
So thus was born photons.
Yes. The idea of the photon was that it discretized what a piece of light. But people had trouble with this because it made no sense when you could describe a photon. You could describe light as being a wave, because waves, it's really hard to discretize what a wave is, at least in the classic mathematical sense.
Okay, so just because they're traveling light.
Yeah.
So just so we're being clear, so what we're saying is traditionally the not necessarily faulty, but the primitive understanding was I turn that light on, there's this wave that just exists between me and the light.
Right.
And it's just this constant wave. And then as we refine it here, we're saying, well, okay, we actually understand that what's carrying the energy of this light is a photon that, we can still measure wave.
Yes.
But it's actually, there's a packet
yes.
of energy that is called a photon that's actually hitting me.
So those two things, right, those two pictures seem to contradict each other, which ends up being one of the interesting weird bits of quantum mechanics is that what you consider a particle has what's called duality. I can look at the light like this, and as long as I'm just trying to say, okay, there's how fast is this thing moving to me? It will look like a wave. But if I want to know, okay, has, a pulse or a bit of the light that I've turned on or off reached me? Has the energy that the wave could be given to me? When I'm asking that, it'll look like a particle. There's a duality between how this object acts based not upon what it is, but how I decide to look at it. That's one of the weird things. And it took people a very long time to, right? There was a lot of resistance on accepting how this picture, this idea could in fact be true, right? People looked at it and said, no. We've got Maxwell. He tells us it's a wave. It should be a wave. How could I possibly ever have anything different than that? And it was actually, entertainingly enough,
so light travels as a wave and interacts as a particle.
Yeah. It was, yeah. So if I'm looking at how it's traveling, right, I'll see wave. If I look at how it interacts, I'll see particle. And that's true, it turns out, of every fundamental particle, everything that makes up the universe, whether it's light or whether it's matter on the table. There is some wavelength that I could talk about and describe to it. But that makes no sense.
Very small.
Very small. That's a picture that particularly the theorists of the late 19th, early 20th century didn't believe, because it seemed counterintuitive. That word showing up again. It was entertainingly, as we talked about at the beginning of this, the work that Einstein did that forced people to have to accept that light and the energy that it could give had to come in discrete packets. So what did he do? He studied something called the photoelectric effect, which was something that was first discovered in 1887. Basically, some dude shined light on some metal as he was trying to do experiments and realized, hey, I've got a spark. And what people realized is, oh, okay, that must be the charge carrier, which I'll call an electron. They didn't have that term quite then. That's the charge carrier that is getting kicked off of this metal just because it's being excited by light. So here's the typical setup.
So 133 years ago, somebody invented the first solar cell.
Yeah.
And had no idea why it did what it did.
Yep. So we have two pieces of metal that are in a vacuum tube and attached to a battery. Right. Little battery boy here. And I have an ammeter so that I can measure current. And it comes in here. So, as you may be familiar with, basically what is a capacitor, if I have a battery hooked up to a capacitor, there's a voltage that matches the battery's voltage between these two plates, right?
Briefly.
Well, if as long as I don't touch the two ends of the capacitor, this is charging the capacitor.
Oh, you got the battery hooked up, right?
This is bad. This is hooked up. All right, so I've got some voltage that's attached here, and if I send in light, what the photoelectric tells me is that something excites, and I will go from no current, right? Because there's no way for anything to pass in empty air, to all of a sudden charge carriers will move across, and there will be some current. So if this, make a basic graph, if I have some light intensity and look at current, then as I increase the current or increase the intensity of the light, the energy that I'm giving into the plate, then I increase the current that the system sees. So the basic idea then is, the light is hitting and this is when we were starting to, at very basic levels, understand some of the very basic structures of matter. So one of the first ideas is, this light must be hitting this piece of metal and exciting. Get rid of that burp. Ugh. It must be exciting the negative charge carriers enough that they get kicked off of that metal and travel across the empty space. Okay, so if I have, for example, the voltage so that it's positive, these things will be attracted towards the plate, right? And form a current. Now, there were a couple of interesting phenomena that showed up in this experiment. Basically, some weird discrepancies, because the idea was, the only thing that matters for the energy, that's coming from light is the intensity, as far as classical theory tells us, right? As long as I shine brighter and brighter light upon the object, I should be giving more and more energy to it, and therefore kicking off more and more photons. And in fact, that's what I see with this basic graph that I first drawn, which is that as I increase the intensity of light, the current goes up. More light, more photons pouring in, more light intensity pouring in, more negative charge carriers getting kicked off, and reaching the other end of the plate, leading to a current. So everything's hunky-dory, right? Now, there were some weird phenomena that popped up. Specifically, so here, if I know I'm doing negative charge carriers, if I have a positive voltage, right, and I can change my voltage by changing the strength of the battery, then no matter what I do with light, then light will, when light causes it to kick
you're
off.
gesturing but not writing.
Sorry, yeah. No matter what I do to this guy, right, as long as I pour it with intensity, it's able to kick off and create more current. But what happens if instead of having the battery oriented this way, positive, negative, so that this plate is positively charged, will accept the electrons? What if I switch it? What if I want it to get away the charge carriers? I change my system so that instead of being a positive voltage there, I make it negative. I make this negative. And what that means is that there will be some electrons, right? Because if I think about it classically, right, the electromagnetism, there is effectively when it's negative, there's an amount of energy that I need to give the charge carrier so that it can overcome the push push away that the plate is putting on the electron, right? Because we know that in electricity, two like charged particles will repel each other. And based on, how negative I make that plate, right, the negative charge carrier coming towards it will feel a repulsion from that. Now, that's overcome by sending it towards that plate faster and faster. If it's not fast enough, it'll get turned away and it won't ever reach the plate. If it's sent, if the little electron ball is given enough energy, it'll smash into it, even though this guy is trying his hardest to push it away, right? So there will be some electric particles that make it through and some that get turned away, right? And the idea is, okay, if light, the intensity of light is the only thing that matters for the energy, then as I'm, giving these electrons energy, that they should all reach the plate as long as I turn up the intensity. As long as I give them enough energy, they will continue to reach the plate regardless of how negative I make it, right? So yeah, classically, more brightness means more energy, which in this case is going to mean a greater maximum speed that I see from these electrons, right? You might have not all of the electrons make it, but there will be some that absorb all of the energy the most and get all the way through. So the idea is that no matter what voltage I choose, there should be some amount of brightness that I can shine on the plate so that I do get a current.
Right.
Right? Interestingly, no. There is a voltage for the light that I'm shooting onto this plate that no matter how intense I make it, the electrons don't make it past. So what that means is, and I should specify in the modern incarnations in the incarnation of the experiment that Einstein was doing, the important piece was to use monochromatic light. Try and make your light as single color as possible. That just gave you the best results, they realized. What Einstein found, or actually what they found, is that there was a voltage, regardless of the amount of light you poured on there, that stopped the light from reaching your plate. And even stranger is that if I, instead of changing the brightness, once I cranked up the voltage so that, no more current was going despite me hitting it with intense light, if I changed not the brightness, but the color of light that I was choosing, if I changed it the right way, I could get current again, which meant I increased the maximum velocity, which means by changing the wavelength, I increased the energy. And they couldn't explain it because as far as classical theory goes, no, I should in fact get the same amount of energy regardless of the color, the wavelength of the light. Because as far as wave mechanics can tell you, right, that wave equation, it's pretty easy to derive that the energy that a wave will send is going to be proportional not to any amount of how much it's fluctuating, but to the amplitude that it's fluctuating at, right? So in this case, the intensity, the brightness, but classical theory had no information, no notion of wavelength or frequency having anything to do with the energy that's contained in that light. And yet what they found is explicit experimental evidence that yes, your wavelength did in fact matter, right? That is what is important to the energy of your system. And the way that Einstein reconciled these facts, right? Because even if you had light that was the right color, you did in fact see the increase in current from increasing your brightness. So you did get more energy from your system, but it was the fact that wavelength did matter that wasn't explainable, right? And Einstein said, wait a minute, I've seen this work from this Planck guy. He talked about the energy of light being discretized, and that solved a problem. Let me try it here. And it turns out if you say, okay, the energy that let's say that light delivers its energy in discrete packets. And so that the kinetic energy of your photon is equal to h mu minus some stopping function, that some potential that's associated with the metal that it has to kick off from. And this perfectly explained the theory. It's the idea that eventually led to one of our most basic ideas of atomic structure, the Bohr model, where I have a positively charged center, and then the electrons have discrete orbits that they can occupy.
And I'm sorry, I missed it. You said kinetic energy is equal to h nu minus
an amount of energy that depends on the metal that you're pulling it from. Basically, metals will hold on to their electrons, so you need to hit them with enough energy to kick it off, right? So if the frequency of the light is too low, you'll get a kinetic energy that's negative that we say, oh, okay, it just doesn't kick off. And that explains why there are some frequencies of light that when you hit it, you don't see any electrons being kicked off. And then when I, need to make sure that my kinetic energy is at least some, EV, some, the charge of an electron times the voltage would be the energy that it would need to overcome that potential barrier from the electromagnetic force. Then if I have some light that's too small to overcome that value, and there you go. I know that light will not, regardless of how much intensity of that light I put onto the thing, will not give you current. But if I have a voltage that is big enough to overcome and match that E stop, that voltage that I've set it to, then I will have current coming through because electrons will be able to overcome the electromagnetic potential that's pushing them away. And so this led to one of the most basic pictures of quantum mechanics that we have of quantum mechanical structures, that basically the electrons occupy these different energy levels that they could have, and there's a minimum amount of energy that needs to be given to jump up from one level to the next. And if I only give you, if a photon comes in and excites, give me yellow. If a photon comes in and excites the electron to only half, then it won't accept that photon's energy. And so the electron won't get kicked off at all. So if I don't have enough energy in my photons, then I can't get that first step. Now I can have, multiple steps of energy coming in, but I have to have at least that much energy. And this was work that was verified again and again. Like I said, it's his first Nobel Prize, is the work that Einstein did on this phenomena, and proposing that, yes, just use Planck's discretized model to describe what's happening in reality, and we can have a principled way of discussing what happens in the photoelectric effect.
And indeed, you could take this a little further and understand the distinction between ionizing and non-ionizing radiation.
Exactly.
Why some radiation levels, it doesn't matter how much you're receiving of that radiation, you're not going to have any adverse effects from it.
Exactly. That's why, we can be fine having cell phones next to us. They are emitting electromagnetic radiation, the stuff that excites photons that, we worry about causing cancer, but it's so low energy, it can't kick off electrons from your body. It can't cause these mutations.
Now, you could, in theory, have 150 cell phones concentrated in one area, and thus it will raise the energy level of many electrons in your body, but all that's going to do is make it hot.
Yes.
It's not actually kicking the electron off,
right,
which is what causes the damaging mutations in DNA.
There's not enough of that energy to kick it all the way off, no matter how much of those photons that you put together.
Right.
Right. Yeah. So we know that h bar, right, that Planck's constant, not h bar, but Planck's constant, which is related to h bar, Planck's constant is something that is a important concept. And in fact,
and that's h.
Yes.
That's super clear.
Planck's constant h. Anytime you have a discretization show up in your work, right? Whenever you're doing physics and something is discretized, right? The Planck's constant will show up and, in fact, be a part of your calculations. In fact, this is where quantum mechanics gets its name, because it was the notion of light, instead of being this continuous wave, came in discrete quanta. And that shift of perspective was so important to the functionality of the theory that the theory got its entire name because of that concept. It's that quantization is what distinguishes quantum mechanics from classical theory. So we talked about how Planck's constant is important, and I made a claim that the Stern-Gerlach machine was in fact a measurement of Planck's constant of h, or h bar, either way. So here's what a typical Stern-Gerlach machine will look like. You'll have a source of some particle and a set of giant magnets oriented, creating for you a slightly inhomogeneous field that you want, and it'll split the particles based on the orientation of their spin. Now, if I were to somehow apply classical theory to predict this, basically what I would say is that, I've got these basically tiny balls of magnets, right? And they're spinning, that creates a magnetic dipole moment. And the way that is orienting will interact with this giant magnet that I have here and cause it to, feel a force, one way or the other. And if I allow for, the arrow to be anywhere being from pointing up to any value to pointing down, then I would expect, this entire spot, right, that I'm detecting on my detector paper to see would be entirely filled in. But whenever I do these experiments on quantum mechanical particles, what I actually measure is this guy here, this thin line of accepted values and nothing in between.
Because those are the discrete possibilities.
Right. And the reason that it forms this ellipse is basically as you get, as it comes through the source, the beam, as something from the source and the beam is off the center axis of the magnets, right? The magnetization will affect it less and less, right? So how does this correspond to a measurement of Planck's constant? Well, all right, let's look. So an electron has what we call a dipole moment. I'll call it. Let me go back to white for ease of view. So I have a dipole moment mu, and that's related to two things. Its gyromagnetic ratio and the orientation of its spin, which I'll call S. Now, the gyromagnetic ratio is simply the ratio of its charge to mass, effectively, for a classically distributed, for a classical object with charge evenly distributed and mass also evenly distributed. It will end up being the...
Because we don't actually know the structure of an electron, so we just assume uniformity.
Right. It'll be half of the total charge divided by its mass. It turns out because of how we go about it, we can find that for an electron, basically because of arguments in quantum field theory, that it is in fact twice its charge, twice the ratio of its charge to, oh wait, what am I doing? No, there we go. Yes, no two. It's just negative. It's just the charge of the electron divided by the mass of the electron, twice what a classical object would say. At the point being, it's a constant, and it's something that we can readily get this constant, right? There's even in undergrad we go through.
What is the little doohickey on the right, top right?
This guy?
No, the top right.
Oh, this. This is
very top, the numerator.
Yeah, that's negative E.
Oh, that's an E.
Is my handwriting that bad? No.
I was like, that looks like one of those little things in Zelda that you beat with the sword and it shocks you.
Oh,
you know what I'm talking about?
I'm trying to like the toric or whatever. I can't remember. It's been a
There
while.
we go. Okay.
Is that more legible?
That's much more legible.
My goodness. So an electron, right, which we'll use for Stern-Gerlach, has the magnetic dipole moment, right? Basically, it's a little spinny.
Buzz blob.
It's little spinning causes this moment that will interact with magnetic fields according to some ratio, and then the orientation that basically that arrow is pointed in. Okay. Now, if I arrange my Stern-Gerlach so that it has inhomogeneous, a slightly inhomogeneous magnetic field, it's going to feel a force. Okay. The force that it will feel will be, again, we're going to get this vector operator, the del, which is basically a derivative in space, right? It's going to be the magnetic dipole moment of the electron dotted with the magnetic field that the Stern-Gerlach machine is producing. Okay. So if I have...
So we can already see a force is going to be applied on the electron based on the strength of the magnet.
So here, because this is quantum mechanics, it's incorrect to talk about a force, but we're going to make a semi-classical approximation to say, oh, okay, this force one way or another will push you either way. So, right, if I have a B field that depends, on X.
And just so we're clear, the doohickeys that you're drawing, those are supposed to be above the...
Those are little arrows, and they indicate that we are dealing with vectors.
Yeah.
Right.
So could you draw one so people can see what they're actually supposed to look like?
What, just what a vector looks like?
It would just... I mean, it's kind of above that B. You could kind of...
Well... What this little arrow is supposed to be? Or
yeah, because people aren't going to recognize the notation when it looks like a curly Q.
Fair enough.
Because these are very common. Like these are equations that you could go look up on Wikipedia, and you'll find these, and then you'll be like, wait, there we go.
Right. So you'll see this. You'll see vectors represented as either normal Latin letters with the arrow on top of them, or boldface letters is what they often show up. But because it's hard to draw bold, and when people are actually writing these things down, yeah, you'll have.
Although it is pressure sensitive.
Arrows that are, but oof,
it's okay.
Oof,
it's okay.
I don't want to.
The arrow is fine.
With as much difficulty as I have just writing this regularly, please.
That's good.
Don't make me have to be even more. All right. So the amount of. So you have a magnetic field that is mostly pointed in, let's say, the Z direction, right? A big field, which we'll call B0, pointed in the K hat direction. And to that, I attach a little bit of inhomogeneity, right? Which I'll call alpha. And it depends on your orientation in the Z, Z direction, what is commonly called K hat direction, but it depends on how far up or down you are. And that inhomogeneity is what lets the derivative operator, still actually survive. Now, in order to preserve one of Maxwell's equations, del dot B being equal to 0, I have to include just a little bit of magnetization that depends on your X direction. But when I actually look at the force, because there's no no baseline driving average force in the X direction, the effect on the particle will be canceled out because of something called Lamar precession happening very quickly. It'll swap back and forth between left and right so quickly that by the time it gets through the magnet, the average effect of that force on it will be 0. So your force overall will be in the Z direction.
It's next to the X. Looks like I hat.
It's a little I hat, and this is alpha, the same alpha that characterizes your inhomogeneity in the Z direction.
The point being, the field is not uniform.
Yes, you make the field be just a little bit not uniform, and that means there's a force. And whenever there's force, what we can do is we can separate and say, okay, the force on this particle will end up then being gamma alpha SZ. And what is SZ? Okay, SZ is...
Wow, you're getting some sass.
I know. I'm sure any actual scientist will be like, how could this person ever think to teach quantum? This SZ is going to be h bar over 2 times this particular matrix, so that if something spin up hits it, a spin up particle, it'll be pushed up. And if it's a spin down particle hits it, it'll be pushed down in the negative direction.
Pretty cool.
Real quick, h bar is simply h over 2 pi. And it shows the over 2 pi shows up so frequently that we just kind of include it in our constant. So let's go back to the picture here. Since I know...
Yeah, that's why we have to learn LaTeX.
Yeah, ooh, man. Since I know the force that the electron is experiencing through here, I know how much it accelerates in one direction. So when it comes out here, it'll, let me change back to black so you can actually see what I'm writing, right? It'll come off here. The up and down results will come off of here at an angle determined by how much force it's experienced across its journey. And that's basically some pretty easy kinematic equations. And if I know how far away, how far away this detector is, then the distance between where the top result goes and where the bottom result is going to be determined by how far away the detector is and how much force the particle experienced. But if I look at my equation for my force, the only thing, and I know alpha because that's what that's how I will know it, because that's how I construct the machine
constructed
itself.
the field that way,
right? I'll know gamma because I have other experiments to determine gamma for me.
Right.
And so the only constant here that I don't know, the only thing that I could possibly be measuring is this h bar. So
Ooh.
a Stern-Gerlach machine gives us a fundamental way to measure what is Planck's constant. What will that value be? And so, as Stuckey say, since this is a fundamental constant of the universe, our principle of no preferred reference frame says, no matter how you measure it, you always get the value of h, no fractions. And we can argue that this is how we can explain the discrepancy between instruction sets and the results that Mermin's device gives you. This is how you explain why Mermin's device gives you the weird probabilities that it does.
And we're saying that it explains it because...
We'll get there.
Oh.
So that's where I'm going to leave it off for now. We will come back. I feel like we've gone through enough. This is the basics.
Damn,
this is the
what a tease.
This is the setup, the history. And when we come back next time, I will take you through some of the fundamental functions of quantum mechanics, some of the things that most matter to the theory, and show how this principle translates into that language. And then from there, show you how Mermin's device is explained. What a crisp physical statement that ends up being: the universe says no matter how you measure it, Planck's constant will always be the same value. And that's that.
All right.
All right.
Well, thank you very much, Ben.
Yeah. I'll see you next time.